Okay, come to the class here. Yesterday, I think we have done something on uh, I equals to dq by dt. Am I right? Yes, yes. So today, better we come to Ohm's law concept. Okay, right. Coming to here, the Ohm's law. Yesterday we have discussed it. To send the current through a conductor, we need some potential difference. That potential difference, suppose increased, current will be increased. So there you are finding out some linear relation. Okay. So that finally we got V equals to I times R, and R is called as resistance. Okay. So today what we focus in which type of materials current flows in conductors only, not in insulators. Okay. So Ohm's law is actually derived for whom? For the materials through which current flows when you maintain some potential difference. That's why it is purely, whether you say or not, purely meant for conductors. Okay. So basically we say Ohm's law should be obeyed by conductors. It is its duty, should be obeyed. Oh, sorry, what is this nonsense? Obeyed by all the conductors. Okay, by the conductors, what actually we are expecting. But problem is, here all the conductors are not obeying the Ohm's law perfectly. Okay, here problem is, few are obeying the Ohm's law, few other are not obeying the Ohm's law. That's why, based on Ohm's law, who are accepting, who are not accepting, we have to segregate again the conductors into two types. Only conductors, keep in mind. Okay. So what we are seeing, the conductors which are obeying the Ohm's law are called, we are segregating, they are called ohmic conductors or simply ohmic resistors. Okay. So if you see here, these ohmic conductors purely they obey the Ohm's law, means basically where we are finding out the difference are, if you ask, what he says here, suppose if I draw a graph between V and I, potential and current. It is like Y equals to mx now. Y is potential difference, X is current. So resistance should be the slope. Okay. That's why it should be a straight line passing through origin. Surely. Why? Because it is in the form of y equals to mx. So actually what we say, the slope here, if I take v on y axis, directly I say in this graph, slope is equals to dv by di. That is nothing but, here I say the resistance. Okay. But problem is here, with the increase of the voltage beyond certain level, means initially looking like V is doubled, current is also doubled, V is tripled, current is also tripled, so resistance remains the same. It is doubled, that is also doubled, means proportionality constant, the resistance is constant. But beyond certain voltage, if you see, if you increase the voltage, the current value slowly not increase linearly, means not going in a straight path. It may go like this, non-linearly. Okay. Non-linear, better I take another color. Non-linearly it may go like this. What happened? Like a curve. Okay. That non-linear relationship you are finding out. Yeah. That non-linear relationship starts from the lower voltages, even at lower voltages. If you see the non-linear relationship, they are called as non-ohmic conductors. Initially, they sustain at least to certain voltages. Okay. Obeys Ohm's law. V looking like a straight line passing through origin. It means V is directly proportional to I. Such type of conductors are called as ohmic conductors. These are ohmic, what we have taken here. So for non-ohmic, if you see there, the graph, it will be appear like this. Almost at the lower voltages, there only the non-linear relationship you can find out. At the beginning only. Okay, not coming to certain voltages. Means you will find some non-linear relation, either like this, non-linear of any kind, even like this, or first increases and then decreases like this. Any kind of non-linear relationship you can find out there. Okay, these are called as non-ohmic conductors. Okay, that's why which do not obey. What happened to it? Okay, right, coming to here, which do not obey. The Ohm's law. Are called non-ohmic conductors. Okay, these are non-ohmic conductors. Then we ask here why they are not obeying the Ohm's law. Even though they are not obeying the Ohm's law, why you are calling like with the word ohmic? Okay, reason behind here is, even though they do not obey the Ohm's law, to find out the resistance at a point, again we use the Ohm's law only, instantaneous resistance, instantaneous slope. Here theta 1, here we say theta 2. To find out the slope here, slope is equals to, generally we write dV by di. Even though that is variable, the slope is variable, we try to find a dV by di as like delta V by delta I, small changes we take, that is equals to instantaneous resistance we take here. And if the resistance is continuously changing here in the formula, if resistance is changed, who is the R here in the formula? Proportionality constant. So if the resistance changes, we are not accepting that R is not a constant. R is a constant, we are not accepting. Okay. If R is not constant, how can you write V is proportional to I none? We should not write. So we have to write it like V is not proportional to I. This is for whom? Non-ohmic conductors. Okay. So non-ohmic conductors, they are not obeying the Ohm's law. Right? Like Hooke's law, Nana, in your first year. Right? Mechanical properties of solids. Within the proportional limit, they obey the Hooke's law. Beyond the proportional limit, they do not obey the Hooke's law. Yes, in the same way. Here, at lower voltages only they obey the Ohm's law, they are ohmic. Even at lower voltages, it is not obeying the Ohm's law. They are called as non-ohmic. Okay. Finally, at high voltages, both are not obeying the Ohm's law. That you have to remember. Why? If you ask, our story starts now. Okay, why they are not obeying the Ohm's law at high voltages? Problem is, if you increase the voltage, Nana, yesterday we have discussed one point. I don't know whether you have remembered, means all of you remember that point or not. I don't know. Yes, why the temperature is increased? Reason behind is the current is produced. Resistance charge here. When the potential difference is increased, by that electric field is increased. Yesterday what we have discussed, this point is equals to minus dou V by dou X. Okay, if delta V is increased, electric field intensity will be increased. By this what happened? Acceleration of electron will be increased. A is equals to E by F. Okay, from F is equals to EQ now. EQ by F is the acceleration. Acceleration is increased. So if E is increased with the increase of potential difference, acceleration will be increased. If acceleration is increased, problem is now starts. What? Suppose here these are the atoms inside the solid. The moving electron, suppose moving in this direction, makes the first collision here. It is stopped by the first atom, and then because of electric field applied in this direction, it is again accelerated in opposite direction. So it tries to move like this and may hit some other atom somewhere here. Okay. And again, accelerates means, look at there, due to the acceleration, quickly it hits the another molecule. And take here, because of acceleration, its quick movement increases. Quick movement increases. Problem is it makes more number of collisions with the atoms. Number of collisions will be increased. Okay, probability of collisions making here inside the substance. Okay, if number of collisions increases, loss of energy at each collision will be increased. Okay, loss of energy is increased, then that is transformed into, every loss is transformed into heat energy. That heat energy finally results to what? Rise in temperature. Okay, so here what he is trying to say, with the increase of all these things, okay, finally the temperature of substance increases. What he said. Okay, this is the problem, Nana. Okay, this is the main important thing. Temperature increases. Okay, when the temperature increases, then what happens again? The vibration of atoms increases. Why? Because they are losing the energy for whom? The atoms only. Okay, so here the vibration increases, then resistance also changes. This is the problem for the conductors. Okay, vibration increases, the chances of collisions, okay, colliding with the atoms increases. Chances are increasing, resistance is increasing. That's why what happens in the next page, I'm going to write, the resistance of conductor increases. So I am going to write here, that implies what happened? That implies of conductor increases. These are interlinked concepts. Okay. So here finally what we are finding out, with the increase of potential difference, number of collisions increases, so temperature increases, so resistance increases. Okay, that happens even at low voltages, they are non-ohmic. Okay, only occurs at high voltages, they are ohmic. That is the simple thing. Okay, so here if you see such type of model, simple example, I think you can say the answer for the question. These two are ohmic conductors. Very simple, and you can say the answer. It is very easy question. Conductor A, conductor B. I am taking the straight lines. That's why surely they are ohmic conductors. Okay. In this case of ohmic conductors, suppose first one makes an angle 30 degrees. Second one also makes an angle 30 degrees, but with y-axis. Whereas here I am taking the current on y-axis and voltage on x-axis. Okay. Now, ohmic conductors means resistance constant. That's why I'm asking what is the ratio of resistances here. RA is to RB. Equals to how much I'm asking. Okay. How much you try to say? In case of VI graph, slope gives what? Is it 3 Srinidhi Priya? 3 is to 1. Srivatsa. Okay. Okay. Right. Good, I think. All of you are right. But here, I think you already observed it is IV graph, not VI graph. So slope gives, in this case, I by V. Ah, yeah, that is 1 by R. Exactly. Right. I by V, that is equals to 1 by R. That is equals to here, that implies slope 1 to slope 2 is equals to inversely proportional to resistance RB by RE. Exactly. So tan 30 by tan 60 is RB by RA. Yes, so here answer will be that implies RA by RB will be equal to inversely proportional means tan 60 divided by tan 30. That is equals to 3 is to 1. So it is a simple question. You see that you only solved the question. Very simple, easy. Okay, even no need to explain. Then here, 1 minute, Nana. Okay, sorry for inconvenience in the middle. Okay, right. Coming to back class again. Here, that resistance depends on what factors, and here the resistance how you calculate with the acceleration, the speed of electron inside. Okay, if you see there, here the electron inside making number of collisions. Once you observe here, number of collisions it makes while reaching from one end to the other end. Okay, but what I am doing at each collision, right, I am assuming that its velocity becomes zero and freshly it starts with zero velocity. Acquired, suppose at first collision the velocity v1. Okay, after making the first collision, I am assuming that its velocity becomes zero and freshly starts from rest and makes the second collision. Strikes with a velocity v2. Okay. If you assume more number of atoms here, makes third collision, makes fourth collision, like again freshly starts with zero velocity and again hits another molecule with a velocity v3 and so on. This is what I am saying. So when it comes from here to there, one end to the other end, it is not moving with constant velocity. Look at there. Okay, that too not even moving with some constant acceleration throughout. Why? Because it is stopped and again accelerates, stopped and again accelerates, stopped and again accelerates, like, okay, with some non-uniform motion you are seeing, like driving the car on the road. Okay, we are trying to accelerate, apply the brakes, again accelerate, again apply the brakes, like the motion is going. So in such case, here to find out the velocity at an instant, okay, we already know the acceleration E by m on the electron in opposite direction to the electric field. We know the acceleration. So to find out V, either you know the distance traveled between two successive collisions or the time taken between two successive collisions. Out of these two, one you must know. Okay, that's why what I am saying here, the distance traveled between two successive collisions is called, anyone remember this name from kinetic theory, Nana? Don't know? Called mean free path. Yes. Mean free path. Okay, represented with the letter lambda. And if you want the time taken to find out, means what I am going to use the formula V is equals to, you already I assumed 0 plus AT. So I require time, or V square minus U square is equals to 2AS. That's it. Out of these two, one I am going to use. Okay. Again here U is 0. V square is equals to 2AS. So yes, already I said this is mean free path. Now I have to say what is T. What is the time, Nana? The time taken between two successive collisions is called, don't know the name, that is relaxation time. Represent with the letter T. Mean free path, infra, mean free path long back. This is relaxation time. Okay. So either mean free path you know or relaxation time you know, you can find out the velocity, right? So V is equals to, either I write root of 2A S is lambda, or relaxation time V is equals to AT, that is A into tau. Generally, I prefer the second equation. Why? Because there is no under root for simplification. That's why I go with relaxation time. Okay. So I can write here at first collision what is the velocity before making the collision. V1 is equals to, I write it like A into tau 1. Similarly, second collision, I write V2 equals to A into tau 2. Okay. Like I write so on here Vn. Right? So on the whole, if you want to find out the average velocity of all these velocities, then average you know how to find sigma v by n. Okay, a into tau n. So here that sigma you observe there, I am going to get a into tau 1 plus tau 2 plus tau n divided by n, means sigma tau divided by n. This is actually named as relaxation time. Okay, the average time taken between two successive collisions. So here we are putting average. Okay, so here this is equals to, I am taking a tau, and this average velocity what we found is called as drift velocity. Okay, Nana? This is drift velocity. So Vd equals to, if you ask, this is one objective question, Nana. What is the relation between average velocity, that is drift velocity, and relaxation time? Okay, I am moving to next page. Do you have any doubts in first and second page, Nana? In Ohm's law or relaxation time, anything? Okay, right, good. Moving to next page here. And we are trying to write the average velocity defined as here is called, we are giving some name to it, drift velocity. Okay. So here, what is drift velocity? If they ask in objective exams, we write like this. Vd is equals to, average velocity is equals to Vd, we write. That is equals to A into tau. A is what? Already we wrote, Nana. E by m into tau. Okay. Now look at here. This is actually average time. That is a constant. E constant. M constant. If you change E, accordingly drift velocity changes. Okay. So that ratio in the next step, if you take, whose ratio? Vd to E. Ratio if you take, this ratio is actually E tau by m. It is defined as mobility of electron inside. So these are all objective points. Drift velocity and relaxation time. What is the relation? What is mobility? It is the ratio of drift velocity to electric field. And what is the relation between mobility and relaxation time? E tau by m. This is called as mobility of charged particle. Here that mobility of electron. Okay. After finding out here drift velocity, mobility, now we have to find out here what is the current and what is the resistance in terms of drift velocity. Okay, Nana? So here, actually what we got, Nana, potential difference is equals to I times R. Okay? Ah. And here, potential difference, generally what we write, minus integral E dot dl, that is equals to I times R. Okay? Ah. So here this is nothing but E is equals to, we can write I upon dl times R. Okay. Now current, once you check, means as we know what I am writing. As we know, I is equals to Q by T kada nana. What we know. So what I am going to write here, that Q is produced by whom? Due to the flow of electrons. So Q is equals to Ne by T. Okay. Where N is what? Number of electrons flowing in 1 second. Where N is number of electrons. What is this? Okay. So here what I am writing, saying the number of electrons in a conductor is not so easy. Okay, why? Because depending upon the dimensions, if I take more length, more electrons will be there. If I take more area of cross section, again more number of electrons will be there. Means if I take more volume, number of electrons will be more. That's why what we do, instead of taking the number of electrons, better you say number of electrons per unit volume. Okay, that one you name it as electron density. Okay, represent with the letter N, small n. So capital N is what? Number of electrons, and small n is what? Electron density. So here in terms of electron density, why don't you say the current? I is equals to get the number of electrons per one unit volume. What I am going to do? Dividing with volume and multiplying with volume. The same equation. Okay. So I am getting I is equals to what? Now I am writing here number of electrons per unit volume replaced with N. Okay. E by time. Volume I am writing here as shall I write area into length, Nana? Area of cross section into length. Volume. Right? Now you check there. I is equals to, I am getting NEA into total length by total time. If the length of the conductor is L from here to there, length divided by time actually gives what? Velocity. But it is moving with non-uniform velocity here to there. That's why if you see there, when it is moving with non-uniform velocity, total displacement by total time, if you write, that gives average velocity. Okay, so this gives actually the average velocity. L by T is equals to the average velocity. That average velocity already defined as drift velocity. So it is equals to Vd. So I got the relation finally. That implies here I write I is equals to the final equation N E A V D. Okay, this is the equation we have to take. Okay, Nana? Who is the Shashanka? Right. This equation you have to keep in mind. Okay, remember one relation used to solve the numericals. Okay, now you see that Vd already you have the equation E by m into tau. Okay, now you can substitute here to get the current and relaxation time. Okay, Nana? So current and relaxation time, here you write, that implies the relation I is equals to, here N E A, Vd is E by m into tau. Okay, finally you are getting I is equals to what? N E square A E tau divided by m. This is the equation what you have to remember for current in terms of relaxation time. So any mistake here, Nana, in this page? Any mistakes are there? Just we try to extract the relations of all physical quantities with relaxation time. Drift velocity, mobility, current, potential difference, resistance, electric field intensity, everything we are trying to derive. Okay, do you have any doubt or any mistake there? You can express. If any mistake is there, you can say. Intra, no one is responding. Are you not able to chat? Then you are not saying anything. Means, do you have any doubt? Srinidhi Priya? Vainavi. Okay. Right. These are different equations. Okay. Now we have to go back to the equation to find out electric field intensity and potential difference. Okay. Before going to these relations here, to use this relation, first of all, how the resistance depends on, why? Because we are getting here in the current area of cross section, means I in the current, it is depending upon the dimension. If area of cross section is more, current is more, what we are finding out here. Okay, means actually if the area of cross section is more, current is more, or drift velocity is less, that's we require some relation. Okay, means it is looking like for a given conductor, number of electrons per unit volume, this is constant, E constant. So I am finding out I is proportional to A into Vd. Right? So next page what I am going to write, that implies here I write I is directly proportional to A times Vd for a given conductor. Why you are taking for a given conductor? Because we took n is constant. Number of electrons per unit volume constant. That is constant for a given element. So constant we are taking here. So for a given conductor, what happens if the area of cross section is changed? So here what I am taking non-uniform cross sectional wire like this, and uniform cross sectional wire, both. For comparison I am taking both. This is uniform cross sectional wire, that is non-uniform cross sectional wire. Where is it? Oh, sorry, that's it. Taking different areas of cross section. Yeah. So if you come to this uniform cross section, here A is constant at all points. So we can say directly I is directly proportional to VD. Okay. But here to send the current won't flow directly kadana. To send the current to a conductor, we have to maintain some potential difference. That is compulsory. So between these 2 points, I am trying to maintain some potential difference. This is the potential difference I maintain. Suppose V is equals to constant. Then for a given conductor, R is constant, resistance is constant. So I can say I is constant here. Okay. So I equals to, if V is constant, I write I is constant. If I is constant, what can I write? VD is constant. Okay. That implies I write here VD is equals to constant. That implies enters, suppose with a velocity, the electron or the current, something enters with a velocity v1 and leaves with a velocity v2. Then I have to say v1 is equals to v2. v1 and v2 are velocities now. Drift velocities are same. Okay. But here non-uniform cross-sectional wire. Okay. Total resistance of the wire is constant. And again I am maintaining some constant potential difference between these 2 points. Okay. In the direction of flow of current. Current tries to flow in this direction from one end to the other end. This is the direction of current flow. And here I am maintaining constant potential difference. Now you check. The resistance of conductor in the direction is constant for a given material. R is equals to constant. So I can have to say I is equals to constant. I equals to constant. Okay. If I is constant, then you have to say A into VD is constant. And it is looking like equation of continuity in first year. Okay. And in first year, I is nothing but here rate of charge flow dq by dt is I. In first year fluids, dm by dt is the rate of mass. So in non-uniform cross-sectional wire, the mass rate of flow is constant, so that A into V equals to constant. In the same way, I is constant, so A into Vd is constant. Means it is analogous concept for the fluid flow. First here and here the current. Okay. Means here you know in the diagram, if the areas of cross-section I gave like A1 and A2, you can easily say that A1 is less than A2 in the diagram. So drift velocities are not same, that we can see. Okay. At the first end, the drift velocity surely be greater than the velocity at the second cross section. Means quickly they enter, slowly they leave to produce the same amount of current. Okay. So to avoid this area of cross section, in the next step, what we do, this is one example, Anna, what I said. I try to find out current flowing through a conductor per unit area of cross section, that is I by A. Now I by A is defined as J, which is called as current density. Okay, so I by A is equals to J. So if you want this current density in terms of again drift velocity or the things, then check back here. Okay, look at the equations. I by A. I by A is nothing but NEVD. So come to here. Okay, that implies I by A, that is J equals to nothing but NEVD. So I am going to get by substituting Vd is equals to EE by M into tau, NE square E tau by M. That is equals to NE square tau divided by M. This is J. Okay. So here for our sake, we are taking a new physical quantity, that is current density, to avoid the area of cross section. Okay. That current density, if you check back here, current density is what? J equals to I upon A. Here problem arised is in case of uniform cross-sectional wire, what you are getting, area is constant. Area is constant, current already it is constant. Then J is equals to total, it is constant through through uniform cross-sectional wire. But Kani, if you see here, J equals to I by A, I is constant, A is not constant. And here J is inversely proportional to area of cross section. A1 is less than A2 or V1 is greater than V2. If you see here, V1 is greater than V2. J is directly proportional to V, velocity. And here you can say J1 is greater than J2. The current densities. Okay. This is the story now. Right? Then, any doubt? One message. Okay, Srinidhi Priya. Right? Mari here, suppose if we select a cross section like this at a point, through the first cross section or through the second cross section or the third cross section, which all the cross sections are parallel to each other. Okay, just like releasing the rings, smoke rings, okay, parallel to each other. Look at through all cross sections, the current crossing remains same. Okay, I equals to constant. But when you come to exam, if they select one cross section at a point like this, suppose if I select a cross section like this, ఏమైందిరా దీనికి ఈరోజు if I select the cross section like this and a cross section normal drawn to cross section here makes an angle theta with the axis, will you say same current flows? No. Yes. Why? Because through this cross section we have to say the current. Okay, then that time what we have to do, at the same cross section like this vertical cross section, if you know J, okay, then J is equals to, actually we derived at like what, Nana? Current per unit area of cross section. Okay, the same thing in reciproc, I write I is equals to J into A. Okay, area is a vector that already you know. Okay, and here I is a scalar, it is a tensor. Okay, behaves like a scalar. To get scalar mathematically, it is inevitable for me to assume J is a vector, there is no other go. Why? Because if I assume J as a vector, by taking the dot product, I scalar. Now you follow, Nana? Here? Yes. So unfortunately, J is becoming a vector. Okay, so here I am saying now that implies J, the current density, is a vector. Okay, and here what I have to say, J is in the direction of current, Nana. Okay, so at least the current tensor direction is helped here to say the direction of J, right, in the direction of current flow. At least the direction of current here helped us to give the direction of J. ఏంట్రా ఇది? In the direction of current. Right? So now look at here. J direction, this is the direction of current flow. J direction and the normal drawn to the area direction, both are not in the same direction. There is some angle. That's why I have to write in the next page, current through this cross section means, I have to write there, I is equals to J A cos theta. If that variable, that is variable, area of cross section is varying, obviously it is varying from point to point. So if you want to write in integration form, I is equals to, I write integral J dot D. This is integration form. Okay, now is clear about the current density, Nana? See here, one to one, we want to squeeze out one relation. That one relation is leading to how many relations here once you check? Okay, actually we tried to find out what the drift velocity. that drift velocity is linked to mobility, linked to current density, here linked to many things. Okay, even J also, relaxation time came. That relaxation time, how it depends on, we are trying to extract all the things. Okay, Nana? Now we have to start. J dot dA. Now we are coming to here the resistance of the conductor, you are saying constant ka sir, for a given conductor. Mari here that resistance depends on the dimensions. How? Why? Because you found that here the potential difference E dot dl, it is depending upon the length. Potential difference. I got the equation. What? Where is it? I here only, sorry. Here only. I is equals to NAVD. Okay, it depends on area of cross section. Mari, is the resistance depending on the things? We have to check. Okay. Mari, if you come to first uniform cross sectional wire, cross sectional wire, if I take, is taken, then I write V is equals to IE times R. V is equals to, I write, in case of uniform cross sectional wire, Nana, I write E into dl, directly I take it as length. Okay, so E into L. Why? Because uniform cross sectional wire, I have to write E into dl, integral dl. If I take E is equals to what we have to write from the equation, Nana, here. Okay, where is from drift velocity, E is equals to E by m into tau. E by m into tau is equals to drift velocity. E is equals to Vd into m divided by E tau. My Vd is same at all points in uniform cross sectional wire. You accepted here. Vd is constant kada nana. If Vd is constant, E constant, M constant, tau constant, already you accepted here. Mobility is a constant. E tau by M is a constant. So Vd is constant, then electric field intensity is also constant. That's why here in uniform cross-sectional wire, E is constant, taken out. So integral dl is nothing but L. The point అర్థమైందా నాన్న? What I said? V is equals to E into L. Why I took? Without taking the integration. All of you followed? Yes? Today new Srivasa not joined. A new student? Harsha, yes. Okay, right. So V is equals to E into L, that equals to I into R. Okay, since I write clearly here Vd is equals to constant in case of uniform cross sectional wire, that implies E is equals to constant. Yeah. E equals to constant. Right, now what I am going to write, E, it is already a constant. So into L is equals to, now I am writing I is equals to NEAVD into R. Okay, whatever I derived, I am going to write here. That implies what you are going to get there. That implies, now you check. E divided by NEAVD into L is equals to R. That implies I am going to get what? E divided by NEVD into L by A is equals to R. So now you check what I separated the terms. ఒక్కసారి check చేయండి నాన్న. All the terms here I separated and kept in bracket are constants or variables in case of uniform cross-sectional wire. All they are constants. Okay, అందుకే ఇక్కడ clearly I wrote E is equals to constant. మీ గురించే ఇక్కడ రాశాను. E is constant, N already constant, E constant, VD is constant, everything is constant. That constant here, all the constants are replaced with a single constant, means E divided by NEVD. ఇవన్నీ తీసేస్తున్నాం, replaced with a single constant. That single constant is represented with the letter rho, called as resistivity of the material. Of the conductor. Okay, idira resistivity. So for resistivity we got one more equation. Okay, so now I think you understood. Cracking advance is far better than mains. All these formulae are important for mains now. We have to buttify like BPC student today. We got many equations in the class today in the class. Okay, now check here from this equation. VD is equals to EE by M into tau kada. Again I am going to substitute VD is equals to EE by M into tau. Okay, or VD by E directly we got there, you check. VD by E is equals to E tau by M. So E by VD is equals to M by E tau. Okay, M by E tau if I substitute. Are you following, Nana? Divided by NEVD. సరే మీకోసం VDనే సబ్స్టిట్యూట్ చేద్దాం. NE కరెక్టేనా? EE by M into tau. Okay, this is EE by M into tau. Sorry, into tau. E is equals to rho. E cancel. That implies rho is equals to, you are getting M by M E square tau. Any mistake here? ఇందులో తప్పేమన్నా నాన్న? Rho equals to this is rho formula for rho. Right? That implies, check there, అసలు ఎనీ వేరియబుల్ ఈస్ దేర్ ఇన్ రో నాన్న. M is constant for a given material, number of electrons per unit volume constant, E square constant, tau is constant. Okay, and all the whole thing, it is independent of electric field intensity developed and it is constant for a given material. Why I am saying specifically for a given material? If material is changed, N is changed. So if material is changed, then N, number of electrons per unit volume, is changed. And what you understood, for a material only rho is constant. If material is changed, rho is also changed. Okay, that implies for different materials, rho is different. Okay, this is rho nana. And you see there what the equation finally you are getting from here. This whole thing is rho. So R is equals to rho L by A in the next page. Okay, that implies we write R is equals to rho L by A. Okay, that in terms of this relaxation time, yeah, rho is replaced with M by N E square tau into L by A. ఇది previously given question in exam. How the resistance depends on relaxation time. Okay. And that implies R is directly proportional to L by A. Okay. R ki now you got the equation now. That you try to substitute in this equation. What V equals to IR. Right? ఇంకెందుకు అయిపోయింది. Already substituted and found this equation కదా నాన్న. అయిపోయింది. So finally we got R is equals to this thing. అయిపోయారా? Everything we interrelated with whom? The relaxation time. Okay. So if the relaxation time is constant, then everything happy. R is constant, rho is constant, VD is constant in uniform cross-sectional wire. Okay, we can say many things. I is constant depending upon relaxation time. But problem is, if temperature is changed, this relaxation time changes. Okay, if temperature is increased, then what happens, Nana? You are assuming that it makes more number of collisions or less number of collisions? More. Number of collisions are increasing until the relaxation time between the collisions. Very good, very good, very good. And previously 10 collisions, 10 seconds. If more number of collisions are there, then relaxation time will be decreased. Very good, very good. So here, if the temperature increases, main disadvantage, relaxation time changes. Okay. So if you come to next point here, when temperature is increased, then what we write? Temperature is increased, relaxation time tau decreases. Okay, If tau decreases, now once you check, that implies 1 by 1. If tau decreases, come from drift velocity. Tau decreases, drift velocity decreases. Okay, I decreases, Vd decreases, I decreases. What we observe from relaxation time. Okay, Vd decreases, tau decreases, J also decreases. We are seeing all these things in uniform cross-sectional wire now. J decreases. And here look at relaxation time decreases. Rho increases inversely proportional. So rho increases. If rho increases, R increases. Hence proved or not, when temperature is increased, resistance increases for the conductors. Hence, by the increase of temperature, resistance increases. Okay, this is what I am trying to say. Actually, I wanted to say today how the resistance depends on temperature. Okay, so my part of job is over. Idostoti. So shall I close the call now, or do you have any doubts? No, no doubts. Okay.